let's build the unit circle. The unit circle is a circle that is centered on the coordinate plane at 0, 0, and it has a radius of 1. So if we are standing out in a field, and this is marked out on a field, and we're dealing with, I guess, meters. We'll go with meters. Then I walk from here to here. How far did I walk? Well, I walked 1 meter because the radius is 1. So anywhere you go from the center, it's going to be 1 if you're going to land on the circle. So we can actually start by naming some coordinates, and I'm going to call my coordinates, so I'm going to color them as red. And so every coordinate that I can easily identify from the very beginning, I'll go ahead and do that. So this coordinate is going to be at, well, 1, 0. And that one's a little trickier, tricky. This one's not quite as tricky. This is going to be 0, 1. And this coordinate right here is going to be -1, 0. And this is going to be 0, -1. If you're not using red, that's fine. But there are going to be several different things that we put on our unit circle. And knowing that we're going to put several different things, I'd like for them to be separate colors just so we can contrast them more easily. Okay, now we need to get to a little bit of other tricky stuff where we have to figure out what these measurements are. And this is going to look a little confusing. I'm going to go about it a little bit differently than most people do and than I usually do. And I'm going to go ahead and give you the coordinates, then I'm going to explain where those coordinates come from. So this coordinate right here is the square root of 3 divided by 2, comma 1/2. That would be this dot right here. So it looks like the arrow is pointing at this. I'm actually referring to this dot, or this dot, or this dot, or this dot. You get my drift. This coordinate is at the square root of 2 over 2, comma square root of 2 over 2. And at this point, there's not much context, and it looks like we're just copying stuff. But that context will be given in just a moment, and hopefully things will click when we do. So those are the coordinates here, and actually knowing the symmetry of this, everything that looks to be the same measurement of an angle actually is. Knowing the symmetry of this, everything that I have in this quadrant, this of course is quadrant 1, I can put it over here, but here my x's are positive and my y's are positive. Here my x's are negative and my y's are positive. So over here, I'm going to put the same coordinate only with the negative x value. So negative square root of 3 over 2, comma positive 1/2, and negative square root of 2 over 2, comma positive square root of 2 over 2, and negative 1/2, comma square root of 3 over 2. A couple quick patterns, fairly easy. I'll point in this quadrant. These are the same. The x and y coordinates here are the same. There's a reason. We'll get to that. And these are reversed. Okay, let's fill in the other quadrants, and then we'll start talking about the obvious things that I've left out, like what angles are we dealing with, which you probably have already seen. So everything I have in the top half gets flipped over to the bottom half, but now I'm going to have negative y values. So here my y's are positive, here my y's are negative. So I'm going to have negative square root of 3 over 2. I want to make sure that looks as negative as it actually is. I'm going to use a little bit of white out here. Not that I wrote it wrong, but I wrote it confusingly. Negative square root of 3 over 2, comma negative 1/2. Negative square root of 2 over 2, comma negative square root of 2 over 2. There I go, running my negatives into my fraction. We'll fix that one. Negative 1/2, comma negative square root of 3 over 2. This one got flipped as well. This one was that. Just got flipped over. Okay. 1/2, comma, negative square root of 3 over 2. This one is going to be negative square root of 2 over 2. Whoa, that's positive. It's positive. Sorry. I messed up just a little bit right there. Negative x value in quadrant 4. That's very wrong. And this is square root of 3 over 2, comma, negative 1/2. Okay, everything looks correct to me. There's the bottom half of the unit circle. And now we're going to jump in with some things that I normally don't have to write in. I'm going to write them in pencil because they're not used in calculus very much. They're going to be angle measurements. And so let's start with the obvious angle measurement. An angle in the coordinate plane is always measured with the positive side of the x-axis being the starting point. So this is my starting ray, you could say, of my angle. So this is going to be a 0 degree angle. I'm using pencil for this one. and this is going to be a 90-degree angle. And if you're thinking, well, what side of this do I write that on? It doesn't really matter, because I'm going to put radians on one side. I'm going to put degrees on the other side, but it's not like this side is going to be 0 and the other side is going to be the radian equivalent. They're both the same. I'm just trying to find little nooks and crannies to put my angles in. Okay, 0 degrees, 90 degrees. This is 180 degrees. And we can keep this thing swinging around here. Basically, it's like this. Let me grab this pair of scissors that was staring me in the face as if it wants to be used for a lesson. There we go. 0 degrees. Well, there we go. We'll do it that way. 90 degrees. And then it opens up. Well, it doesn't open up any further. But this is the beginning. And then the angle ends here, or here, or here. All right, 270 degrees here. And then we're actually back to 360 degrees here. So 0 degrees and 360 are the same. By the way, 270 was down there if you couldn't see where I had it. I'm going to zoom out just a little bit. You can see a little bit more of what's going on there. There we go. I think that'll make it a little bit easier to see. There's been a couple times where you've not been able to see what I'm writing. Sorry about that. Okay, let's fill in some of the other angle measurements. We'll use degrees first, and the big angle measurements are going to be 30, gaps of 30 degrees, and the little ones are going to be 15. So we're going to count by 30s and 15s. So from 0, adding 30 is going to give me the obvious 30. Let's add 15. That's 45. Add 15 is 60. This is what we have in quadrant 1 so far. We'll keep counting. We add 30, we're at 90. Add 30, we're at 120. Don't care which side you write that on, it really doesn't matter. Add 15 is 135. Add 15 is 150. Add 30, 180. Add 30 is 210. Add 15 is 225. 240. 270. 300 degrees. 315 degrees, 330 degrees, and then we're at 360. Okay, this is what we have so far. And now we're going to fill in a different type of angle measurement that you have undoubtedly seen before. It's called radians. Radians is another way of measuring angles, but it has everything to do with the circumference of the unit circle. And again, this is a unit circle. Obviously, it's the title of the lesson and it's what we're filling in. But it is also the, again, length of the radius. So if I was to say to you, hey, I walked from here to here, how far did I walk? Well, I walked 1 meter. If this is measured in meters, I walked 1 meter. Well, how far did I walk here? 1 meter. How far here? 1 meter. Now we get to a trickier question that's not as tricky as you may think. How far did I walk if I walked all the way around the circle? And I've asked this in classes before, and I get all kinds of crazy answers, but here's the big idea. I'll write it on this Post-it note, and you know this, and this is going to look super familiar to you. I'm dealing with the circumference of a circle, and the circumference of a circle is 2 times pi times my radius. My radius is 1, so I have 2 times pi times 1. So if I was to walk all the way around the circle, I just walked 2 pi meters in this case. So going from here all the way around to here would give me a radian measure of 2 pi. I'm going to put radians in blue now that I have a blue pen in my hand. So 0 degrees is 0 radians. 360 degrees is 2 pi radians. It ends up in the same place as 0, of course. So I would have walked 2 pi, around 6.28-ish meters, if I walked all the way around here. So 6.28 meters. Well, if I only walk half of that, I didn't walk 2 pi's, I walked 1 pi. So this is pi, and again, it doesn't matter which side of this line you're writing this on. 180 degrees is pi. They're all the same thing. Okay, well, let's fill in the top half. If I walked around here, I went to pi, or I walked a length of pi meters, 3.14-ish. If I only walked up to here, I didn't walk the full pi, I only walked half of a pi, so pi over 2. Let's keep cutting this in half, at least for this part. If I walked this length, I walked pi over 2 meters. If I walked half of that, I'd walk half of pi over 2. That wouldn't be half of a pi, that'd be a fourth of a pi. I think we can fill in some of the other aspects of this fairly obviously. So I'm going to count by 1/4 of a pi. So I'm walking. I walk here and I walked 1/4 of a pi. I walked another 1/4 of a pi, so 2/4 fourths. I hope you just visualized in your head what I just said, because I just said 2 fourths, which is a half. Notice that's half of a pi. I walk 2 fourths of a pi. I walk 3 fourths of a pi. 3 pi over 4. I walked 4 fourths of a pi. And again, here's a fraction that visualizes in your head. I just walked 4 fourths of a pi. Well, that's 1 pi. Let's keep walking. I walk 5 fourths of the pi. Of a pi. That's more than a pi. I walk 6 fourths. No one says 6 fourths. Everybody calls it what it really is in its reduced form. That would be 3 halves. So I walked 3 pi over 2. Okay, so 5 pi over 4, 6 pi over 4, 7 pi over 4. And then 8 pi over 4. 8 over 4 is 2. All right, well, we've got a lot of the angles. Well, we got all the angles filled in with degrees. We now need to finish filling them in with radians. So let's fill in the rest of these, the ones that aren't labeled yet, and then we'll put some other crazy stuff in there. And I'll tell you where all these other red numbers came from that seem to come out of nowhere. So this 30-degree angle is, well, let's kind of count. Okay, if I wanted to go from here to here, I went to pi, right? I'm going to walk from here to here, I walked pi. Well, if I only walked this much of it, how much of it did I walk? So let's count this space. 1, 2, 3, 4, 5, 6. Oh, okay, so 30, and we can do this mathematically. 30 is a sixth of 180. So if I'm dealing with 1/6 of 180, I'm really dealing with, well, a sixth of pi, so pi over 6. Let's count by sixths. Now, as I say it, I'm going to write the reduced form instead. So 1/6, 2/6, that's a third, 3/6, 4/6. Notice I'm saying one thing and writing something else. 5/6. If I have to reduce it, that's what I do. 6/6. I'm going to zoom in just a little bit more. Lower that just a wee bit. I'm going to go down to the bottom half. You can see it a little more clearly. Pause it if you need to see something. 6 over 6. 7 over 6 pi. 8 over 6 reduces. That would be 4 pi over 3. 8 over 6. 9 over 6. Already there. Already reduced. 10 over 6. 11 over 6. There we go. Okay, we have a little bit more that we're going to do, and I want to explain where these numbers in red came from, and I also want to put some other numbers on there. There's a lot going on in this thing. So here's what's really happening. This coordinate right here was not just made up out of nowhere. I'm going to trace it just a little bit. You'll be able to see it very roughly. If I was to draw this right here. Okay, we just decided this was a 30-degree angle, right? It's a 30-degree angle. And I wanted to know this coordinate. I want to know that, what that was, which we already know, but I'm about to show you where it comes from. Let's say that this is 1, because it's 1. Whoops, that's not 1. This is 1. My fault, sorry. The actual radius right there was 1. Then I need to figure out what everything else is. Let's expand this idea just in case you haven't seen the special right triangle that's about to happen. There's a lot packed into this. This is called a 30, 60, 90 triangle. But just so you'll know where all this comes from, I'm not making this up. If I was to draw this, I would have an equilateral triangle. And I know it's equilateral because this is 90, that's 90, this is also 30, so I have a 60. This is going to make this 60. 60. I have a 60, 60, 60 triangle, so it's equilateral. So this is 1, this is 1, and this entire piece right here is 1, which makes this 1/2, makes this 1/2. And I can use the Pythagorean theorem to figure out what that distance is, and I'm going to. So if I don't know what that is, we'll call it A. So A squared plus 1/2 squared equals 1 squared, which is kind of pointless. A squared is 1/4. 1 minus a fourth is 3/4. Square root that, and I would do the plus or minus thing, but I'm dealing with a distance in this case, so we'll just go with the positive. There we go. So this distance right here is the square root of 3/4. So if I wanted to know, sorry, square root of 3/2, sorry. If I wanted to know this coordinate, I would say, oh, well, that's it, square root of 3 over 2, comma, 1/2. So just so you know, that's where that comes from. Let's do a little trig while we're here. This is going to be great. If I walked up to you and I said, hey, what's the sine value of 30? What's the sine of 30 degrees? Now, I could also call it sine of pi over 6. And now that we're dealing with calculus, we're going to be dealing with radians. But in the meantime, let's still stick with degrees. So sine of 30 degrees. What's the sine of 30 degrees? Well, it would be opposite over hypotenuse. I'm ignoring this triangle down here. Opposite over hypotenuse, that'd be 1/2 over 1. 1/2 over 1. I'm not going to put it over 1. So the sine of 30 degrees is 1/2. Look, there's your 1/2 right there. This is the sine value. If I said, hey, what's the cosine of 30 degrees? You would say, oh, well, that would be adjacent over hypotenuse. That'd be square root of 3 over 2 over 1. Let's ignore that. So there's your cosine. There you go. Now, I say there you go as if we're done. We're not. There's more. This is my cosine. This is my sine. For any value on the unit circle, it's going to be cosine, comma, sine. So up in the corner, I'm going to make that little key. So cosine of my angle, I'll use theta, Greek letter theta. Sine of my angle, there we go. Any x value here is a cosine. Any y value is a sine. So we figured out where this one comes from. We figured out where, well, the corresponding ones come from. This is the reverse of that because I could draw this triangle differently. I'm not going to go into that in this video as much as I would love to. Very quickly, I do want to show you where this square root of 2 over 2, square root of 2 over 2 comes from. And let me grab this pen. Here we go. Thanks for letting me grab that pen. Appreciate that. That's very helpful. This was 45. That's 90 degrees. Not drawn very well. This is also 45. That's 1. Here was isosceles, so these two are the same. I'd call them A and B, but they're the same. I'm going to call them A and A. So A squared plus A squared equals 1 squared. Let's not square it because it's 1. And I have that. I would divide by 2. And I'll square root this, so I'll have A equals the square root of 1, which is 1, the square root of 2, which is that. That does not look like what we wrote, but it's about 2. Back in the day, we did this a whole lot more when we had to divide more by hand, but we would do what's called rationalizing our denominator. Square root of 2 in the numerator, 2 in the denominator. So that's where this coordinate comes from. All right, now that we know where the coordinates come from, I want to show you one other cool trick that you may or may not have seen before. It's going to lead to what we're going to do on the back side of this. Everybody knows this. Everybody knows this. The tangent of an angle is equal to opposite divided by adjacent. And we also know a couple other things. We know that sine of an angle is equal to opposite over hypotenuse. I'm just doodling here. You don't have to write this down. Cosine is equal to adjacent over hypotenuse. Let me slide it up so you can see. That'd be helpful, wouldn't it? So let me walk you through this. I'm going to aim for opposite over adjacent by using these. Follow me on this. If I had opposite over hypotenuse and divided by adjacent over hypotenuse, then the hypotenuses, hypotenuse, I guess, would cancel. I'd have opposite over adjacent, which is tangent. But if I do opposite over hypotenuse, I really have sine. Now I do adjacent over hypotenuse, I really have cosine. So in case no one ever told you, tangent is equal to sine divided by cosine. Now that's going to come in handy more on the back side of these notes. Some random accent just kicked in. But the sine over cosine is equal to tangent. That's going to come in handy. So I'm going to grab another scrap piece of paper, and we are going to figure out the tangent values for every one of these. Told you there's a lot going on here. And let's see, what color have I not used? I haven't used green. Let's use green. My tangents will be green. Sorry to go off on a tangent. But what I'm about to do is divide every sine by cosine. And when I divide sine by cosine, I'm going to get tangent. And notice where I pointed. I'm going to divide every sine by cosine. I'm going to divide every y by every x and get a tangent. Okay, so let's go for the obvious. 0 divided by 1 is 0. Okay, I'm going to go for some obvious ones first. I like to hit the obvious. I go for the easy things first. Low-hanging fruit is what I call it. That one looks tricky. We'll deal with it later. it's manageable. But square root of 2 over 2 divided by the square root of 2 over 2. Anything divided by itself is, well, 1. Well, 0 divided by 0 is not 1, but we'll play that game later. 1 divided by 0 is not 0, and it is not 1. 1 divided by 0 is undefined. If you ever graphed a tangent, you probably saw that it was undefined at pi over 2. There's an asymptote there. Okay, let's finish this top part with the easy ones, the low-hanging fruit. Square root of 2 over 2 divided by negative square root of 2 over 2 is negative 1, and 0 divided by negative 1 is 0. Okay, let's tackle some of the harder ones. Let's do this one right here. By the way, once we get this one and this one, we'll be able to just flip it over and do the bottom as well. It's going to be easy. So what I'm doing is taking sine, the y value, and dividing it by cosine, the x value. And let's go ahead and cancel the 2's because you can. So I have 1 divided by the square root of 3. That's fantastic. I like it. You're right. We're not wrong, but I'm going to keep going because we rationalize denominators in this town. So we have the square root of 3 divided by square root of 9, which of course is 3. So this tangent is square root of 3 over 3. And we'll deal with this one as well. This one's a lot easier. Sine divided by cosine. Cancel the 2's again, and it gives me the square root of 3 over 1, which of course is the square root of 3. There it is. Almost finished. Here's what we're going to do. We're going to transfer these to all the other quadrants, almost said coordinates, well, the coordinates in the other quadrants, by using the appropriate signs, S-I-G and S. So notice that this corresponds to this. I'm going to zoom out a little bit more again. There we go. This corresponds to this. However, if I was to figure this one out, like I figured this one out, I wouldn't be doing positive divided by positive. I'd be doing positive divided by negative. So this one's going to have a negative sign. And same thing here. This corresponds to this, so this is negative square root of 3. Let's slide up. Everything we have in the numerator, it's not a fraction. Everything we have in the top half of the unit circle goes to the bottom half. And I have to watch my signs, S-I-G and S, as I do that. Let's go for the obvious here, undefined. Can't divide by 0. I tried once, it didn't work. This is that, only if I did it, I'd have negative divided by negative, which is positive. This is positive. This is positive, and these are negative. Okay, almost finished. Almost finished. Something I want to point out, one big pattern that's going to come in handy later. I want to see where things are positive and where they are negative. And I say with the things, what things am I referring to? Well, here in quadrant 1, everything's positive. Cosine is positive, sine is positive, tangent's positive. Anywhere you look here, you see no negatives whatsoever. So they are all positive here. Notice it looks like a big plus sign. It's still a coordinate plane. Work with me here. I want to know where things are positive. They're all positive in this quadrant. In quadrant 2, let's see who's positive. Let's see, tangent's negative. Cosine is negative, but sine is positive. So in this one, sine is positive. Let's put an E on that just for fun this time. Spell it right for once. Abbreviations here. There's quadrant 3, there's quadrant 4. In quadrant 3, who's positive? Let's see. Well, cosine's not, sine is not, tangent is. So tangent is positive here. And in quadrant 4, who's positive? Cosine is positive, and only cosine. So, quadrant 1, all are positive. Quadrant 2, sine is positive. Quadrant 3, tangent's positive. Quadrant 4, cosine is positive. Here's what a lot of people do. ASTC, and they have little mnemonic devices to remember that. A lot of them say things like, all students take calculus, which is totally not true. But if you want to remember it that way, you can. All students take calculus, or all students, I don't know. I can't think of anything else off the top of my head. But there you go.